Okay, let's finish off integrals. So we started talking about the change of variables formula last time. We never got to the formula, but we started motivating it, and we figured out we should worry about limits, and we realized if we used nice change of variables, we're not too worried about the limits doing ridiculous things on us. We should still have a set we can integrate over. And then we started asking, but what about what happens to the dx essentially? Right? How does our transformation change volumes? And we worked it out for all linear transformations. So now we've got to say, what does it actually do finally to our integral, which involves possibly a nonlinear transformation, but a well-behaved nonlinear transformation. So let's try to finish this off. All right, so we're trying to do an integral over some set. And we don't really like the variables that we're integrating over. So we say we want to make some kind of substitution. There's two ways that you may find it natural to do a substitution. One is you say, I'd really like to replace x with something else. The other thing that you might see, and we saw this in the little 1D example last time, we said, actually, we'd really like to replace x squared with something else, and we substituted for x squared. So you might see something like this, or you might try to do something like this. Okay, and these two guys should just be inverses of each other, right? So in fact, we have both of them. You know, you may naturally write down one or the other, but we have both of them. So we've got some set that we started with, t, and the points in here we call x. And then we say, well, x we're going to call g of y, and this is going to take us to some other set, and maybe either this other set is simpler, or the integrand becomes simpler, or something. And our variables are y here. And we have the function f that takes us the other direction. Okay, we're not worried about, at this point, we're not worried about this being a bad set. We kind of worked out that as long as we start with nice regular transformations, nothing bad is going to happen. So what we just need to do now is say, how do I rewrite this integral in terms of an integral over s? So I'm going to do this for the case where s is a rectangle. That shouldn't worry you at all. We kind of know that once we can do rectangles, we can do anything. So I'm assuming s is a rectangle. Nothing bad happens if it's not. All right, so let's let s be a rectangle. Now, we know it's going to be important. How does this thing change volumes or areas? We know it for a large collection of transformations, but probably not this one. We only know it for linear transformations. If we're going to pull this off for nonlinear transformations, we kind of have to zoom in on a small scale, because locally this thing looks linear. So as long as we're only worrying about this on a small scale, we're probably in business. So what I'm going to do is partition my rectangle, and then I'm going to do a lot of integrals over little rectangles. So I'm not doing it at this stage. I'm not trying to do a Riemann sum. I'm just partitioning it so that I have to do a lot of exact integrals over tiny regions where my transformation looks linear. Okay, so let's let P be our partition. So this is a partition of our rectangle. Okay, so we do something. Okay, and when we look at how this thing transforms into my other set, each of these little subrectangles is also going to morph into something, and together they'll fill up the volume of T, and they're not going to overlap with each other because we have a nice invertible transformation that we're working with here. So I'm going to take my set t. It's going to be whatever it is. I'm just going to draw it to look almost like a rectangle just for ease of drawing. And it's going to do something like this. Okay, and again, we're going to have a partition, I guess, if you like. It's not a real partition. These aren't rectangles, but they're subdivided into little chunks. And if this rectangle here is Rj, we're going to say that this gets mapped onto some little set Tj, which again is not a rectangle, but together these Tj's don't overlap except at the boundaries, so they're going to do all the nice things we need them to do. Okay, so let's let Tj be defined as G of Rj, the image of the jth little rectangle. Now the integral I want is the integral over this whole set, but since these little guys don't overlap, right, their overlap has zero content, doesn't contribute to the integral, I could equivalently integrate over this, plus this, plus this, plus this. And then what I'm going to try to do is relate it back to integral of this, plus this, and hopefully now on a small scale my transformation looks linear and I can do things kind of easily. Okay, so what we're actually after, we're after this integral, and now I'm not doing any approximations here. This is exactly the sum of the integrals over all the Tj's. All right, and now I need to try to do some kinds of estimates. Now what can I work out? I can work out kind of approximately the volume of these little blobs, right? If I assume this is small and if I assume G is basically linear here, I can work out the volume of this little blob. So I can work out the integral of a constant over this little blob, approximately, we hope. I'm waving my hands here, but I'm trying to come up with a strategy. This is not a constant, but let's make another reasonable assumption. Let's suppose we're working with a continuous function. If I'm working with a discontinuous function that has a discontinuity in here, this is going to be hard to start estimating what's going on. So let's work with a function that we know that we're in business with. Let's suppose that f is continuous. Of course, if we had a piecewise continuous function, then we could decompose our domain into regions where it's continuous and do separate integrals that way and still maybe pull off our change of variables. And if we had something that's pathologically non-continuous, then we're probably in bad shape anyway. So this is not such a bad assumption. What does that do? That lets me use a mean value theorem for integrals to say this is basically equal to f at some point times the integral of the constant function. I like the integral of the constant function. That's just the volume of my blob. The volume of my blob, I think I can maybe estimate. So this, we're going to say, is f of xj times this. Okay, for some xj in the blob. This is our mean value theorem. And now we're just looking at the volume of Tj here. All right, so it's now the volume of Tj that we have to compute or at least approximate. Right? Approximation is good enough because then we'll take a limit where we make this partition arbitrarily refined, and hopefully the errors go to 0. So how am I going to estimate this? I've got to use the fact that G is differentiable. I've got to work with this linearization. All right, so let us define the linearization of G. All right, so where am I going to do this about? Right now, I have a reference point over in here, but G acts on things that live over here, right? So I need to find a point over there to linearize about. Well, I should probably use the point that corresponds to xj, right? Xj comes from somewhere. So if I draw a picture again, if this is my, say this is my tj, and here's my xj. This came from a particular, this came from a particular rectangle. And the xj came from a particular point yj. Okay, so we know there exists some yj in this rectangle such that xj equals g of yj. And it's unique because we're working with a regular invertible transformation. Okay, so if this is the reference point showing up here, it probably makes sense to linearize about this reference point right here. Okay, so L of y is going to be this linearization. It's going to be g at my reference point plus the Jacobian of g at that point times y minus yj. Okay, and now good news, g is differentiable. G kind of looks like this locally. Now we got to make precise what I mean by that. Since g is differentiable, we said that, well, the precise meaning of that is that the limit of g of y minus L of y divided by y minus yj goes to 0. Okay, so if I want to say g of y is approximately L of y, so that I can try to use the volume that comes from L, well, let's make that precise. We know that if we choose an epsilon bigger than 0, I'm just writing the definition of the limit. The usual thing I do, I see a word, I see the word limit, I'm just writing out what it means. No magic. All right, we know that there exists some delta greater than 0, such that if y minus yj is less than delta, let's put a 0 here, then all of this, right, is less than epsilon. So if I rewrite this a little bit, g of y minus L of y is less than epsilon times the length of y minus yj. Okay, so I would certainly like to be in the situation where y minus yj is small, less than delta. Y lives over here. Y lives in the rectangle. So that's good. I can control how small that is, right? I don't have immediate control over how big distances are in here. I mean, I kind of do through G being Lipschitz. But I have immediate control over distances within Rj. I just need to refine the partition until no 2 points in this rectangle can be farther apart than delta. Okay, so I'm just going to say this diagonal, right? This diagonal has to be at most delta. Okay, so let me just refine our partition. Okay, so that y minus yj is less than delta for every y in that same little rectangle. All right, and as long as I'm there, I can use this inequality, this estimate. I can say that g of y, my transformation, looks exactly like this linear transformation plus an error that is bounded. It's at most this. Okay, so instead of using this g here, I'm going to use this L, and L is going to take a rectangle and make it into either a rectangle or a parallelogram or something, right? We worked out all the possibilities, basically. It's going to do something simple, and it's going to give me some little blob here. Okay, so this is, I'll call this TJ tilde. TJ tilde is sort of an approximation of my actual shape, but it's an approximation that I can work out the volume of. The TJ tilde will be the linearization applied to acting on my little rectangle. Whereas TJ was the actual nonlinear transformation acting on things. All right, now how different are these really? Well, here, length scales in this rectangle are on the order of delta. All right, that means length scales here are also on the order of delta, right? Times some constant, maybe. It depends on the Lipschitz constant, but basically this length scale is like delta. The lengths here also scale like delta, but it's not going to be exactly the same as the lengths up here. There's going to be some little error in it. How big is the error? Well, the error is going to be at most epsilon times, well, this is at most delta. So the error along each dimension is going to be at most epsilon delta. Okay, so if we think about the amount of, the amount of overshoot that we have maybe, say that our little bit of error here, this really scales like epsilon delta at most, times some constant. So more or less, this is a bit hand wavy, but each side length of TJ tilde has an error that scales like epsilon delta. So that means if I try to compare the volumes of these two things, right, this is a simple shape. This deviates from a simple shape, but the deviations are smaller on the order of epsilon delta. So I have some little extra mass that I'm overcounting or missing. But that's on the order of epsilon delta. Okay, so what kind of errors am I making at the end of the day? If I'm making this kind of little epsilon times side length error on each side, when I add those up, I'm going to get a factor of epsilon to the n when I multiply them together. So this is going to be bounded by some constant times epsilon n times the actual volume. All right, I'll pause a second. Questions? Right, basically the volume of this is side length times side length, and then the volume of this is going to be side length plus order epsilon times side length plus order epsilon. So that's where this epsilon to the n times the overall volume comes in. Well, this guy we know. Right, in terms of the volume of Rj, we know this. It just changes the volume by a factor that depends on the Jacobian of this guy, right? Well, the Jacobian of this guy, because this guy is linear now. Okay, so since Pj tilde equals L of Rj, and L is linear, we know that we're just going to get the volume of our rectangle times the determinant of L, of the Jacobian of L, at some reference point. I mean, the Jacobian is constant, it's linear, times the volume of our original. And what's the Jacobian of L? It's just a Jacobian of G at this reference point, exactly, right? This is a constant, there's no y's in here, it's a fixed point. This matrix is also a constant matrix, and then times a linear term. So when we take the Jacobian, we just pull out this constant matrix. So this is the determinant of the Jacobian of G at our reference point. Y's, yeah. Okay, so what do I want to do? I want to try to feed that information back into here. This was the integral we were trying to do. Oh, we said, well, we can write it in terms of the volume of these little blobs. And now we know that the volume of these little blobs looks a whole lot like this, plus some error that looks like this. So we can quantify this fairly precisely at this point. Okay, so this was, I'll just write this again. And now let me use my mathematician's favorite trick of just, sticking in the thing that I would rather have here and then subtracting it back out again. J equals 1 to k of f of xj, volume of t tilde, and then whatever is left. All right, this guy. All right, this guy we know what it is, right? It's all of this, which is now in terms of y. That's not a bad thing because at the end of the day, we're hoping to turn this into something that looks like an integral over y. So really, we should be trying to get all of this in terms of y. That's fine. We can do that. We have a nice correspondence between x and y. We made the substitution. X is g of y. So that part is easy to work with. Okay, so I'll make this f of g of yj. I'm going to put in my expression for the volume of this object, which we know exactly what it is. Determinant of the Jacobian of g at yj times the volume of my little rectangle. Plus whatever is left over. This looks not so bad as my candidate for the real answer. Actually, this kind of object has a special kind of name, which we've seen before. I'm summing up over all these little rectangles of, well, something evaluated somewhere in each rectangle times the volume of the rectangle. What is it called when we do that?
Integrating.
It's almost integrating. It's a Riemann sum, right? It looks like the integral. So that's good. That looks very much like an integral over that set that we want, over this rectangle. So this I'm kind of happy with. I think when I take limits, this is going to converge to an actual integral. And then here's whatever error is left over, and we hope that as we refine our partition, that error goes to 0. We think it will because we've got pretty tight bounds on what this is going to do. Okay, so let me write, on the left-hand side, I'm just going to rearrange things. This is the integral I want to do. On the right-hand side, I'm going to move over this object. Okay, so f of g of yj is determinant of the Jacobian of g times the volume of the rectangle okay, and this is going to be bounded by the biggest possible value of f times whatever this difference was. F, we made an assumption at some point that f is continuous. So this isn't going to do anything ridiculous on us. Certainly it's bounded, right? If we're trying to do an integral, if we're trying to do a Riemann integral, it's bounded. Okay, so let's suppose that m is the maximum of f on our domain. The maximum is okay here because we started with a continuous function. Maximum of s and x on the closure of s, I guess. Just to be careful. So what is all of this less than or equal to? It's less than or equal to m times the sum of this error in our volume, which was some constant times epsilon n times the volume of these little t's. And what happens when I sum up the volume of these little t's, tj's? Yeah. I just get the total volume, right? None of this stuff depends on j. So this is nothing but, some constants times epsilon n times the total volume, which we know to be finite because we started with a bounded nice set. We used a nice regular transformation. We're going to get another bounded nice set. So a bunch of stuff that is finite and fixed, these are constants, times epsilon to the n. And as epsilon goes to 0, what's the statement we want? If we're interpreting this as a Riemann sum, so this is a Riemann sum, this is our candidate for the limit of the value of the integral, and we want to say that that can be laid less than any epsilon or than anything that goes to 0 with epsilon. Okay, so this right-hand side goes to 0 as epsilon goes to 0. So we've actually recovered here the definition of Riemann integrability. This is a Riemann sum of something. This is the value of the integral, and this is the less than epsilon or epsilon tilde part. So we can actually say, great. We've actually recovered here that, what are we doing in Riemann sum? This is f of g of y times the determinant Jacobian of g of y. We're doing an integral over s or r. They were the same thing. And that is equal to this. This is sitting in here as our limit. So this is precisely what we were after. We wanted to take this thing and write it, do a change of variables, write it in terms of an integral over this other set, S. Questions? Yeah.
For that term, after the epsilon and delta, where does the volume come in again?
Where does the volume come in? I erased the picture, but I'll give you a new picture. So what we had here was, we had something that's not quite simple. This was our TJ. And the linearization gave us something that's nicer. And if I put these on top of each other, they're almost the same. And the deviations in the boundary are going to be on the order of epsilon times the side length. Right? So if this has side length, say, L, okay, then the deviations that we're going to get here, okay, I'm going to write this. The deviations are going to be on the order of epsilon times L. And that's true for every side. So at the end of the day, V of Tj is going to look like, we multiply all these together, we get our total volume, but with this little epsilon error in it that gets multiplied out. So it's going to look like, L plus L epsilon or CL epsilon to the nth power, or there might be different L's along each dimension. But at the end of the day, it comes out as, L to the n plus something on the order of epsilon to the n, multiplying this. So something on the order of L to the n, epsilon to the n. Okay, so that lets us write this down as a theorem. So I'm just going to rewrite it with all the conditions that we assumed, because it's good to always remember we make assumptions. Okay, so here's our change of variables theorem. Let's let G be a nice transformation. Okay, on compact, Jordan measurable set. Okay, and we assume that F was continuous. Let's give this set a name, S. And let F be continuous on G of S. Okay, then it's completely equivalent that integrating over the set G of S okay, so this we called T before, but T was precisely the image of S under this transformation G. And this is the same as integrating F of G of Y times the determinant of the Jacobian of G of Y in absolute value. All right, are we reasonably happy with the theorem? All right, let's do an example or two. Okay, so let's assume that the integral we want to do, I'm going to give it a name I, so that I don't have to keep writing the whole thing, is the integral over the set t, e to the x squared minus y squared squared, e to the 4x squared y squared times x squared plus y squared dx. And the set t is going to be a part of this annulus at least, where x squared plus y squared is between 1 and 4, and x and y are both non-negative. Okay, so our original set is something like this. That's not drawn to scale. All right, and let me label the variables. And I don't know about you, I don't want to sit down and do this integral in its current form. So we want to see if we can make it simpler. There's not one right way to go about these. There can be multiple changes of variables that will all lead you to the right answer. But I guess the rule of thumb is I'm going to come through here and just start looking for some kind of key terms that show up. So I mean, one thing that shows up here is x squared minus y squared, so that might be a natural thing to try as a variable. There's also this 4x squared y squared, which is the square of 2xy. Since this is something squared up here, maybe I want something squared up here, because I guess I'd rather have a u squared plus v squared than a u squared plus v. I don't know. You can try things, and if it doesn't work, you try something else. But basically, whatever the key terms that show up there are probably a good choice of your variables. So let's try to identify some important terms. So I'm going to suggest to try u equals x squared minus y squared and v equals 2xy. I have to, with this change of variables, be able to figure out what my new domain of integration would be. So I have to work out what kind of limits I would have for these using this information. Here I can see v is going to be non-negative for sure. I need to figure out something else here. Let's see. So one thing that I might try to do is add the squares of these two things, which are going to be important anyways. Because I think when I add the squares of these two things, I'll be able to factor it into something that looks like this. So if I just try something like this, u squared plus v squared, what do I get? I get x to the 4th plus y to the 4th minus 2x squared y squared plus 4x squared y squared. And that looks factorable. X squared plus y squared all squared. Okay, so if x squared plus y squared is between 1 and 4, then this quantity is going to be between 1 and 16. So this is between 1 and 16. And we said it looks like v has got to be also non-negative. Okay, so here's the transformation that I've noticed. I've noticed that I mean, we said we can go two ways. We can identify a function of x and y, or we can say we want x and y to be equal to something. Here I've identified it as a function of x and y. That's often what naturally pops up, but not always. Okay, so we've identified f of xy as x squared minus y squared and 2xy. Okay, so f is going to go this way. F is a function of x and y. G, which is important because we need the Jacobian of G. G is going to be the thing that comes back. We've got our UV variables here. And what do we know about them? We know that u squared plus v squared is between 1 and 16. So once again, we're looking at part of an annulus with radius between 1 and 4. And we're going to be looking at just a particular half plane, right, where v is positive. So here's u, here's v. V is positive, so we're only up here. And then we're going to be looking within this annulus. And this is the set that I want to be integrating over. Okay, so if that's the set that I want to be integrating over, so t equals g of s, we've worked out what s is. Okay, so s is the set of all u and v such that u squared plus v squared is between 1 and 16 and v is non-negative. So the integral we want to do, all right, we've got the integral we want to do in this form, all right, integral over t is what we want, and t is the image of s under g, so that's good. Okay, and now this is going to be the integral over this new set s. F of g of uv. And those things I can substitute in for okay. Because here I got a u that pops, u squared here, v squared here, x squared plus y squared. We figured out a connection between x squared plus y squared and my uv variables. So all of that I can substitute for, that's not a problem. Then the other thing that I need is this determinant of the Jacobian of g. So how do I get the determinant of the Jacobian of g? Inverse function theorem, thank you. So I mean, one option would be figure out what g is, right? Figure out the inverse of this. Solve for x and y in terms of u and v. That doesn't look like a fun thing to do. Of course, nowhere, we said without knowing g explicitly, we can make the substitution. We saw that. We picked our variables carefully so that it would be easy to make the substitution. Then I don't really need the whole thing. I just need the determinant of this Jacobian, this like one number. And the inverse function theorem tells me that actually the Jacobian of g is related to the Jacobian of f in a particular way, and their determinants are just going to be reciprocals of each other. So I don't even have to invert the matrix. I just have to work out the determinant of the Jacobian of this and take its reciprocal. Okay, so if you happened to naturally identify g here, then you would just work out its determinant as Jacobian. But if you happen to naturally identify f, then you probably don't want to do that. You probably want to do inverse function theorem. So inverse function theorem is going to tell us that the determinant of the Jacobian of g is nothing but 1 over the determinant of the Jacobian of f. And that's not so bad. That we can probably work out. Okay, so Jacobian of f is going to be 2x minus 2y, 2y, 2x. Okay, again, inverse function theorem tells me the Jacobian of G is the inverse of this matrix, but I don't need the whole matrix, happily, so I don't even have to invert the matrix. All I need is its determinant, and the determinant of the inverse matrix is the inverse of the determinant. So the determinant of this is going to be 4 times x squared plus y squared. So the determinant of the Jacobian of G is going to be 1 over 4x squared plus y squared. And by a happy accident in the way this problem is set up, this is actually going to cancel out this part. So even if I couldn't find an easy way to substitute for this part, it will cancel with this Jacobian. So you don't have to immediately panic if there's things that look hard to substitute for. If you're lucky, you'll get some nice cancellation. Or if the person who wrote the problem is kind, you'll get some nice cancellation. Okay, so let's go back to the integral that we're trying to do. The integral that we're trying to do is now the integral over S. All right, this is u squared, this was v squared. All right, here we saw something that we said was going to cancel. So I have this x squared plus y squared divided by all of that. Everywhere you see an x or y, you want to think of that as, xy is equal to g of uv. Okay, so it looks like there's x's and y's mixed in there, but implicitly this is all in terms of u and v. I wouldn't be able to just say, let's pull these out of the integral. They depend on each other. But happily, this simplifies down quite a bit. And we get something that looks prettier than what we started with. I still don't really want to integrate it in this form. So we might need another change of variables. This may happen. In principle, I guess we could get this all through guessing one clever change of variables at the start. We didn't do it. But we simplified things, so now it's maybe not so hard to guess an appropriate change of variables here. Polar coordinates, right? This looks like a radius squared. This has some beautiful circular symmetry going on here. So that'll be natural to express in polar coordinates. So let's do another change of variables using polar coordinates. Okay, so this time I'm going to naturally substitute for u and v, the things that appear in the integral. So we're going, before we kind of naturally identified the thing going this way, now we're going to naturally identify the transformation the other way. So it can work both ways. So we write down our polar coordinates. Okay, give this a name. F and G are used up, so I'll call this H. What's our domain? Our domain is going to be, well, the radius goes from 1 to 4. Angle goes from 0 to pi. Our domain's actually a rectangle now. Okay, so we started with half of our annulus. Okay, we've got u and v written as a function of r and theta, so h goes this direction. And now over here we have just our rectangle. So here's 1, here's 4, here's pi. I don't have to worry so much about the transformation going the other direction, right? I guess as a rule of thumb, if you can't remember which thing you're taking the Jacobian of, the determinant of the Jacobian of, because I don't know about you, but I always forget which one is it. You want it also pop up in your new variables, right? So you want something here, we want something at the end of the day that's in terms of r and theta. H is in terms of r and theta, it's a function of r and theta, so this is the thing we want the determinant of the Jacobian of. Okay, so here we don't need inverse function theorem, now we can just do it directly. Jacobian of H is, right, derivative with respect to r is cosine theta minus r sine theta, r cosine theta. All right, and the determinant of this is r cosine squared plus r sine squared, that's just r. Okay, so let's try to do our complicated integral that we started with. So the integral that we started with was the integral over S, which is the image of this rectangle, of e to the u squared plus v squared. Okay, so let's change our variables. We're going to integrate over r. U squared plus v squared is r squared. We need to include this determinant of the Jacobian, which is in the correct variables. So we did the correct Jacobian. Okay, and then dr theta. And now everything is continuous and beautiful, and we're looking over a rectangle, so we can do an iterated integral and work this out, and I'll just give you the final answer. You know how to do this. Questions? So, that is an example that probably shows you everything you could ever hope to or fear that you might see. I'll also mention, let's come back to polar coordinates and do one other example. I always have stressed that when we use a theorem, there are conditions on the theorem, and we have to satisfy the conditions if we're going to use the theorem. It's unfortunately easy to break the conditions of this change of variables theorem, but it turns out it's often not a problem. So let's do polar coordinates again, and let's try to work out the area of a disk. Okay, so we have this set S. Do I want to call this S? Let me call it T. And I just want to integrate the constant function over this disk. This seems like a good use of polar coordinates. Just obvious. You're never going to get more circular symmetry than we have here. So polar coordinates. So we go, all right, r cosine theta, r sine theta. Our set S is 0, 1. Right, radius goes from 0 to 1. Now we're going all the way around the circle from 0 to 2 pi. Okay, and we can write down what is the Jacobian of G and what is all this stuff. G is continuously differentiable, certainly. Okay, so we're not going to have any particular issues here with the integral over S of this guy. This integral exists, and we can certainly do the integral. And I would like to use the change of variables theorem to say that this and this are the same. Now, do you see any problems? What are the assumptions that we made for the inverse for the change of variables formula? Okay, things are Jordan measurable. That seems to be true. Yeah. We assume G is regular. Regular, part of that was invertible. There's a problem here. I have some periodicity going on here. And if I plug in theta equals 0, or I plug in theta equals 2 pi, I get the same value back. So this is actually not regular. So this is our big problem here. So G of R0 equals G of R2 pi. So this is not regular. Now, it turns out this doesn't kill us. We can still use polar coordinates for the entire disk. But it's just always worth being careful. Here we need to use little approximation arguments where we say, right, what we're trying to do, we're trying to have this rectangle where the radius goes from 0 to 1 and theta goes from 0 to 2 pi. And what we'd like to do is use that to get at our disk. Now, the only problem happens with theta equals 0 and 2 pi, okay? If we exclude those, then we don't have a problem. Okay, so the real answer here is just to say, let's start with a slightly smaller set. So let's take a little delta here and a little delta here. And let's work with slightly smaller sets. Okay, so I've taken a little bit off of my delta, off of my radius. So we're going to exclude a little bit out here, a little bit in the middle, and I've taken a little bit off of my angle. So I'm also going to exclude a little bit of this. Oh, not here, centered on the axis. Let's try that again. And as soon as you make the set a little bit smaller, g is regular again on this smaller set. And the integral that you want to do over here is equal to the integral that you want to do over here. And then the short answer is you can just take limits and say, but the area, the volume I've excluded is negligible. G, Jacobian of G, it all stays bounded. Okay, so it's not going to contribute anything to the volume, to the integral. So the short answer is you could do approximation arguments. Okay, so we use the change of variables formula on a smaller rectangle, maybe from delta 1 minus delta to delta and 2 pi minus delta, on which g is regular. And then you argue that the leftover bits will integrate to 0 as we take delta in a limit to 0. So I'm not going to go through all the calculations. It's not that hard to go through it. But I just want to bring this to your attention because I keep stressing, check the hypotheses of your theorem before you use them. It's really easy to write down cases like this where the hypotheses break slightly. It's usually not a big deal, but you should be aware of these kind of issues. And again, typically you could make an approximation argument like this that says, as long as there's just a small number of points, essentially that's it. There's a small number of points only where there's a problem, right? The set of points where there's a problem has 0 content, right? And the function is not doing anything stupid at those points. So they shouldn't contribute an issue, and you can argue that rigorously. Okay, and that means, we can go up to higher dimensions if we want to and say, compute the volume of a sphere. So if our set is a sphere of radius A, then we can introduce spherical coordinates here, which are not going to be regular for the same reason, but the issues happen at just this small set of points, right? A set of points of 0 content. And the functions that we're working with, the transformations we're working with, they're nice. So we're not so worried. So with spherical coordinates, we say, okay, we want to introduce this transformation, rho theta phi, And we have rho cosine theta sine phi, rho sine theta sine phi, and rho cosine phi. Usual spherical coordinates. So rho is our radial component that goes from 0 to A. Okay. We have theta as this azimuthal angle that goes all the way around the circle. And of course, the periodicity here is what breaks the regularity, but only at a small number of points. And then we have this polar angle that goes from 0 to pi. So suddenly we're integrating not over a sphere, we're really just integrating over a box, a three-dimensional box. Right, and at that point, what are we trying to do? We need the Jacobian of this. This is in our new coordinates that we want to integrate with respect to, so it's the Jacobian of this that I need. So we do the Jacobian of all of that, cos theta sine phi. Rho sine theta cos phi. Hey, rho cos theta sine phi, and rho sine theta cosine phi. And then I have a cosine phi, 0, and a minus rho sine phi. Okay, and we take the determinant of this. I'll let you check that on your own time, and we get something like rho squared sine phi. The negative sign doesn't matter. We're going to take absolute values of everything. Okay, so then at the end of the day, we're just doing an integral over a box. And this is the little change of volume thing that tells us how the volumes of our little boxes change in the transformation. So the integral that we really want is the integral over our original set, or over our original cube, or over our original sphere, sorry. And now we're just integrating over this little box. And since everything is nice, we can do iterated integrals. And that makes a quantity that would be hard to guess if you didn't have the formula memorized, which perhaps you do. And we can work out exactly the volume of a cube. Okay, and of course, we could do functions with an integrand here, right? Doing the, it's this part that's the hard part. It's the hard part to compute and remember. But if we had an integrand here, we could put the change of variables through there with no extra work, hopefully. But big picture is, you take a look at your structure of your problem. If you see important variables that look hard to work with, but they're kind of important, that's what you try substituting for. Then you want your Jacobian in terms of, as a function of your new variables. So it's either you have that, or you use the inverse function theorem to get you there. And that's change of variables, and that's about all we have for integrals. So then, from here we're going on to chapter 8, which is where we get to do some fun new things with metric spaces, to try to break down your intuition a little bit. Your intuition was formed in 3 dimensions, and now we're going on to more bizarre spaces. But I'll leave you there today, and we'll pick back up next week.